You expect the power to be there, like you walk into a dark room, you flip a little piece of plastic on the wall, and the room just instantly floods with light.
Yeah, it feels completely binary, just on-off.
Exactly. But if you were to actually look behind your drywall, like trace that copper wire all the way back to its origin, you wouldn't find some simple battery.
No, definitely not. You'd find this hydrogen-filled sparking metal leviathan just spinning at like 3,000 revolutions per minute.
Held together by these microscopic electrical balances. It is wild.
It really is. I mean, it's the ultimate hidden, highly choreographed mechanical ballet. The sheer scale of the engineering required just to keep that one light bulb glowing for you is staggering.
Well, welcome to the deep dive. Today, we are opening up the schematics. We're diving straight into an incredibly detailed text on electrical power engineering, specifically the hidden anatomy of a massive power generation station.
Right, we're tearing apart the electrical section to really figure out the how and the why behind these colossal machines, the ones that keep our modern world from, well, going completely dark.
Yeah, and by the time we finish this, you are going to completely rethink what happens behind the walls when you simply turn on your television.
We're stripping it all down to the studs today, from the synchronous generators at the core to the intricate systems that wake them up.
The massive transformers, too.
Yes, and the totally unexpected role of massive battery rooms. It's an ecosystem where every single component relies perfectly on the delicate physics of the others.
So let's start at the absolute heart of the beast, right? The core of any power plant is the synchronous generator.
Right.
Because this is where the physical motion of a spinning turbine is actually translated into the electricity that flows into your home.
And to really picture how this works, you have to look at its two fundamental anatomical parts. You have the rotor and the stator.
Okay, rotor and stator.
Yeah. So the rotor is the spinning part. It is a massive cylinder of solid steel physically coupled to the turbine shaft. But to make electricity, that spinning metal needs to become an electromagnet.
Right, it needs a magnetic field.
Exactly. So it is fed a direct current DC voltage, which is transferred into the spinning shaft via carbon brushes.
Wait, let's pause right there because that detail alone is kind of wild to me.
Oh, yeah.
Yeah. You have a massive steel shaft spinning 50 times a second. And to get electricity into it, you have physical blocks of carbon just physically pressing against a ring on that spinning shaft.
Yep.
That's pure friction. I mean, it must be sparking and wearing down constantly.
Well, it's an incredibly harsh environment. Those carbon brushes are what we call sacrificial components.
Meaning they're meant to be destroyed?
Basically, yeah. They are designed to slowly wear away while maintaining that critical electrical contact at incredibly high speeds.
Wow.
Now, while that rotor is spinning like crazy and acting as a giant magnet, the stator surrounds it, and the stator is completely stationary.
Hence the name stator. Stationary.
Exactly. It's built out of thousands of thin, compressed sheets of silicon steel, and they're all insulated from each other by a mineral called mica.
Okay, got it.
So as the magnetic field of the rotor sweeps past the coils in that stationary stator, alternating current is finally born.
Okay, so you have this immense magnetic field, thousands of amps of electrical current, and, as you said, intense physical friction.
Yeah, a lot of friction.
That combination creates the ultimate enemy of heavy engineering, which is heat.
Right.
Like, if you let that heat build up, electrical resistance skyrockets and the insulation literally melts.
Yeah, you completely lose the machine.
So how do they deal with that?
Well, the plant utilizes parallel cooling systems to fight it. The stationary stator is cooled by demineralized water flowing through it.
Demineralized water. Why demineralized?
Because demineralized water doesn't conduct electricity, so it's perfectly safe to run right next to high voltage. But the spinning rotor requires something completely different.
And this is where the engineering gets slightly terrifying, in my opinion.
I know exactly what you're going to say.
To cool the rotor, they use hydrogen, as in the highly explosive gas that destroyed the Hindenburg.
That's the one.
Why on earth would any engineer look at a multi-million-dollar metal tube filled with sparking electricity and think, you know what this needs? High-pressure explosive gas.
I mean, on paper, it sounds like a recipe for a total disaster. But the laws of thermodynamics actually make it the perfect choice.
Really? How so?
Hydrogen possesses an incredibly high thermal conductivity. It can absorb heat and carry it away from the spinning metal far faster than regular air ever could.
Okay, so it cools things quickly.
Right. But there's a second equally important mechanical reason. Hydrogen is the lightest element in the universe. Its density is incredibly low.
So, meaning there is less physical air resistance.
Exactly. Imagine trying to run through a swimming pool versus running through the open air.
Right, totally different drag.
Right. When you have a massive metal cylinder spinning at 3,000 RPM, the aerodynamic drag, the wind resistance, is immense. By replacing the heavy air inside the generator casing with lightweight hydrogen, you drastically reduce that friction.
Oh, that makes sense.
Yeah, that simple swap saves megawatts of power that would otherwise be wasted just fighting the air. Plus, hydrogen happens to be a phenomenal electrical insulator.
It's the perfect coolant, assuming you ignore the tiny detail that it likes to explode.
Well, hydrogen is only highly flammable if it mixes with oxygen.
Oh, okay.
Inside the generator, it operates in a sealed, closed-loop system containing essentially pure hydrogen. There's no oxygen to burn.
So the real danger emerges if that seal fails.
Yes. If outside air leaks in and the hydrogen mixes with more than 14% oxygen inside that enclosed space well, then the generator basically becomes a bomb.
A single spark from those carbon brushes we mentioned earlier would cause a catastrophic explosion.
Exactly. Which means the engineers had to design some pretty intense safety protocols.
Yeah, and the source material mentions one emergency sequence that is just fascinating.
The venting process, right?
Yeah. In the event of a dangerous leak or a fault in the seal, they don't just, slowly bleed the gas out. They trigger a rapid ejection system.
Right, they violently vent the high-pressure hydrogen straight up into the open sky, far above the plant, and any possible ignition sources.
Right, and in Egyptian Arabic, the text notes this rapid emergency venting is actually known as the Tafnit process.
The Tafnit process.
Yeah, you basically blast the explosive gas into the stratosphere before your multi-million-dollar generator turns into a bomb.
It's extreme, but absolutely necessary.
So, okay, now we know how the beast generates power and how it survives its own heat. But as I was reading, I hit this massive logical paradox.
The chicken and egg problem.
Yes, we said you need to pump DC power into the rotor to create the magnetic field. But wait, if the power plant is completely dead and the grid is offline, where are they getting the electricity to make that magnet work in the first place?
It is the ultimate bootstrapping problem, honestly. Because to generate alternating current in the stator, you absolutely must have a moving magnetic field.
Right.
And that magnetic field relies entirely on an electrical feed from what is called the excitation system.
Okay, and the excitation system isn't just some small battery you can buy at the store.
No.
It relies on a secondary generator called the exciter, which sits on the exact same spinning shaft as the main generator.
Yes. And its entire existence is dedicated to pushing about 500 volts and a massive 5,000 amps into the rotor just to keep that magnet alive.
But the exciter is a generator itself.
Exactly.
Yeah.
Which means it also needs a magnetic field to start generating that 5,000 amps.
It's literally an ancient riddle. Which came first, the chicken or the egg?
Exactly.
Here's where it gets really interesting for me, because it's like an old car. You need the engine running to turn the alternator, which charges the battery. But to start the engine, you need a jolt of electricity from a small battery to turn the starter motor.
It's a closed loop.
Right. So how do power plant engineers solve this loop?
They do it by introducing a third, much smaller machine at the very end of the shaft. It's called the permanent magnet generator, or PMG.
The PMG.
Yeah, this is the key that unlocks the paradox. The PMG produces a relatively small voltage, only around 100 volts, but the crucial detail is in the name. It uses a permanent magnet.
So it doesn't need to be excited by an outside electrical current.
Exactly.
Its magnetic field is just an inherent physical property of the metal itself.
Precisely. It requires zero outside electricity. As soon as the massive turbine shaft physically begins to rotate, that permanent magnet spins.
And because the field is already there?
Because the field already exists, it instantly induces a small electrical current. That small current wakes up the exciter.
Oh, wow.
Yeah. Then the exciter takes that spark, amplifies it into a roaring 5,000 amps, and shoves it into the main rotor. And just like that, the giant wakes up.
That is so elegant. But wait, once the main generator is awake and it's pumping out hundreds of megawatts, what happens to the tiny PMG that started it all?
It basically bows out.
Really?
Yeah, once the main generator is running at full capacity, the plant actually reroutes a tiny fraction of its own massive output back to feed the exciter.
So it feeds itself.
Yes. The PMG is disconnected from the active circuit, and the entire system becomes fully self-sustaining.
That is brilliant. But, the external grid isn't static, right?
Oh, not at all. It's constantly fluctuating.
Right. Like, If everyone listening to this suddenly turns on their air conditioning at the exact same time, the demand on the grid spikes, and the voltage naturally wants to drop.
Absolutely.
So how does the plant handle that without the whole system crashing?
Well, it relies on a piece of hardware called the Automatic Voltage Regulator, or AVR.
The AVR.
Yeah, it's basically an electronic brain that monitors the main generator's output thousands of times a second. If the voltage on the grid starts to sag, the AVR immediately steps in by communicating with a component called a thyristor.
Okay, let's unpack that really quick. What exactly is a thyristor?
Think of a thyristor as a microscopic, ultra-high-speed floodgate for electricity.
A floodgate.
Yeah, alternating current travels in a wave, and instead of just opening or closing a valve, the thyristor can actually chop that electrical wave into pieces.
Oh, fascinating.
Right. By adjusting what engineers call the firing angle, the thyristor dictates exactly how much of that wave is allowed to pass from the exciter into the rotor.
So if the voltage drops, the AVR tells the thyristor to open the floodgates wider.
You got it.
More current flows into the rotor, the magnetic field instantly becomes stronger, and the main generator pushes the voltage back to where it needs to be.
Exactly. It is a microscopic, high-stakes balancing act, and it's happening in milliseconds.
Okay, so we solved the magnetic field riddle,
Yeah.
but we actually skipped over a pretty massive physical problem.
Oh.
Yeah. We said that PMG only works if the shaft is turning.
Right.
How do you physically rotate a massive gas turbine, something that weighs hundreds of tons, from a dead stop?
That is the million-dollar question. Because a gas turbine cannot just start spinning on its own. Before you even introduce a single drop of fuel, the compressor section must be running at high speed to pull in and compress massive volumes of air.
And turning hundreds of tons of stationary steel requires a staggering amount of physical torque.
It really does. And the startup sequence for this is completely counterintuitive. They don't have a giant pull cord, obviously.
Right.
The plant actually pulls power from the external grid to start itself up. They take high voltage electricity from the 220 kilovolt transmission lines outside.
Wait, they take power from the grid?
Yep. They bring that grid power into the plant, run it through a startup transformer to step the voltage down, and feed it into a medium voltage 6.3 kV bus bar.
Hang on, a bus bar.
Oh, right. Think of a bus bar, like the massive multi-lane highway of the power plant.
Okay.
It's a thick, solid copper bar that acts as a central hub, consolidating and distributing huge amounts of electrical current safely.
Gotcha.
So from that bus bar, they feed the electricity backward into the main generator.
I need to make sure I'm hearing this correctly. They push electricity backward into the exact machine that is supposed to be making it.
I know, it sounds completely backwards, but it relies on a beautiful piece of physics formulated by Michael Faraday.
Okay, Faraday.
A generator and an electric motor are essentially the exact same machine, just operating in reverse.
Wait, really?
Yeah. If you turn a shaft mechanically inside a magnetic field, it generates electricity. But if you pump heavy electrical current into those stationary stator coils, the magnetic forces will reach out, grab the rotor, and physically force the shaft to spin.
Oh, wow. So by feeding the grid power in backwards, they basically temporarily turn a multi-million-dollar power generator into the world's largest electric motor.
Exactly. They use it as a colossal starter motor. The magnetic forces grab the hundreds of tons of steel and force the compressor to start spinning.
That is wild.
And it spins faster and faster, sucking in huge amounts of air. Only when the compressor is moving fast enough and the fuel is injected and ignites in the combustion chamber does the turbine finally start producing its own physical torque.
And once there's an actual fire driving the turbine, do they just abruptly flip a switch to turn it back into a generator?
Oh no, it is incredibly delicate.
I figured.
Once combustion is sustaining the rotation, they disconnect that external grid power. The spinning shaft accelerates until it hits its exact rated speed, which is usually around 3,000 RPM.
Okay.
But before they can connect it back to the grid to push power out, they have to synchronize the phases.
What does synchronizing the phases actually mean in this context?
Well, alternating current is a wave, right, with peaks and troughs.
Yeah.
And the power grid has a specific rhythm.
Right.
If the grid is at the peak of its wave and the power plant connects while its own generator is at the trough of its wave, the physics clash violently.
Ooh, that sounds bad.
It would be like trying to jam two rapidly spinning gears together when the teeth aren't perfectly aligned. The electrical shock would instantly translate into a mechanical shock massive enough to literally snap that solid steel turbine shaft in half.
Oh my gosh, so they have to perfectly match the rhythm of the grid before they lock in.
Exactly.
What's fascinating here is how incredibly vulnerable this whole sequence is.
Very vulnerable.
If this beautiful backward starting process relies on the external grid already having power, what happens if there's a total blackout?
Yeah, that is the ultimate nightmare scenario for a grid operator. Because if there is a complete grid failure, there is no 220 kilovolt power to pull from.
Right.
You cannot run the generator as a motor. The entire power plant is just a giant dead hunk of metal.
Which means to reboot the modern electrical grid, you still have to rely on an old-school internal combustion engine.
Yep.
To perform what they call a black start, waking the plant up from a totally dead grid, they fire up a colossal 20-megawatt diesel generator.
It's math.
Imagine a locomotive engine kicking on, just to provide the initial spark to run the pumps and turn that massive shaft for the very first time.
It really grounds you in reality, doesn't it? Beneath all the elegant electromagnetic physics, we still occasionally need a giant roaring diesel engine just to turn the key.
We really do. Which actually brings us to a huge geographic problem.
Oh, the transmission line?
Yes. Once we have this Leviathan spinning and making power, we have to get it to the people.
Right.
If the plant is generating electricity at, say, roughly 23 kilovolts, and the city is 300 miles away, you can't just send 23 kilovolts down the wire.
No, absolutely not. The electrical resistance of the transmission lines over that distance would cause almost all the power to just burn off as heat before it ever reached a single home.
Right.
You have to push the voltage incredibly high, up to 220 or even 500 kilovolts, so it can travel those long distances efficiently.
And historically, plants bridge that gap by using massive main step-up transformers.
Yeah.
Giant house-sized machines that take the 23 kV and boost it. But why is the generator stuck at 23 kV to begin with? Like, why not just generate transmission-level voltage directly inside the machine?
That's a great question. And the limitation has always been structural geometry.
Geometry.
Yeah. Inside a traditional stator, the copper conductors, the actual wires carrying the current, have a rectangular cross-section, like a flat bar.
And in the world of high-voltage electromagnetics, sharp corners are your worst enemy.
Right, exactly. Think of electricity under pressure, sort of like water in a hose. If the hose is perfectly round, the pressure is evenly distributed against the walls.
Makes sense.
But if you try to push incredibly high-pressure water through a square pipe, the physical stress concentrates intensely at those sharp 90-degree corners until they eventually burst.
Wow.
Electricity acts the exact same way. The corners of a rectangular conductor cause the electric field to spike intensely right at the edges.
So if you cranked it up,
If you tried to generate 400,000 volts in a rectangular wire, that concentrated electric field would instantly rip through the insulation, cause a massive short circuit, and totally destroy the generator.
wow.
That geometric limitation is exactly why traditional plants cap out around 23 kV.
Well, enter a revolutionary engineering leap, the Powerformer.
Yes.
Conceptualized by the Swiss company ABB back on February 25, 1998. This machine can generate up to 400 kilovolts directly out of the stator.
It's incredible.
It completely eliminates the need for that massive, expensive step-up transformer. So how did they suddenly break the 23 kV speed limit? What changed inside the machine to solve the corner problem?
Well, they solved it by just getting rid of the corners.
Really?
Yeah, the Powerformer swapped out the rectangular conductors for cylindrical cables, and they insulated them with XLPE, which stands for cross-linked polyethylene.
They just made the wire round.
I know, it is an agonizingly simple but brilliant fix. A cylinder has no edges, therefore it creates a perfectly uniform electric field all the way around the cable. Because the stress on the insulation is spread out evenly, they can crank the voltage all the way up to 400 kV without destroying the machine.
And the downstream benefits of just making the cable round are staggering. I mean, plant efficiency increases by 1.5%.
Which is huge.
Right, to a casual listener, 1.5% might sound like a rounding error, but in heavy power generation, gaining 1.5% efficiency on hundreds of megawatts running 247, that translates to millions of dollars in fuel savings.
Absolutely. Plus, you completely eliminate the cost and the maintenance of those giant transformers.
The source specifically cites a study on a hydroelectric plant in India that proved exactly this. They replaced 4 traditional generators and 12 massive transformers with just 4 Powerformers, and their total cost has dropped by nearly 24%.
It is a profound simplification of the process. You remove an entire intermediate step that requires massive cooling systems and intense ongoing maintenance.
But the reality is the vast majority of current power plants aren't Powerformers yet.
No, not yet.
They still rely on traditional setups. They still have those massive transformers, which get so incredibly hot they require dedicated cooling systems.
Oh, yeah.
We're talking setups with 22 separate oil coolers and 8 giant industrial fans just to keep the main step-up transformer from melting itself into slag.
It's a lot of infrastructure.
It is. But as I was reading about all these systems, it was actually the low-voltage systems that really caught my eye, specifically the DC battery room.
Ah, the unsung heroes.
So what does this all mean? Why does a massive plant that generates hundreds of millions of watts of alternating current dedicate so much space and money to a room full of direct current batteries?
It all comes back to that blackout scenario we talked about. If the grid fails and the main turbine trips offline, the plant is no longer generating power.
Right.
At that exact moment, every single AC system in the facility dies. The lights go out. But far more importantly, the heavy machinery stops.
So the DC batteries are the absolute last line of defense.
They are the brainstem of the plant. They power the critical control systems and the protection relays that safely isolate the damaged equipment.
Wow.
But the most terrifying physical reality is the turbine shaft itself.
How so?
Well, we have hundreds of tons of steel spinning at 3,000 RPM. It takes a long time to spin down to a complete stop.
Oh, right. It has momentum.
Exactly. If the AC-powered lubrication pumps die, that massive steel shaft will instantly run dry on its bearings. The friction would tear the machine to shreds.
Oh, man.
Yeah. The DC batteries are there to keep emergency lubrication pumps running until the beast finally comes to a safe rest. If the battery room fails during a blackout, you lose the entire multi-million-dollar plant to catastrophic physical destruction.
The stakes are astronomical.
They really are.
And just like the Powerformer, this battery technology is completely reshaping the industry. The text mentions that in China, some power plants have actually entirely removed their emergency diesel generators.
Which is wild to think about.
Right. Instead of relying on a mechanical diesel engine to perform a black start, they're using massive, warehouse-sized arrays of DC batteries to spark the plant.
Yeah.
There's a specific 15-megawatt plant they mentioned that performs this black start entirely off solid-state battery power.
It requires a tremendous amount of physical space, but it points to a massive evolutionary trend. The industry is desperately trying to move away from moving parts.
We've covered an incredible amount of ground today. We started with the explosive paradox of using hydrogen gas to keep a sparking machine cool.
The Tafnit process.
Yes, we untangled the ancient chicken-egg paradox of magnetic fields relying on the quiet, inherent power of a permanent magnet.
Right.
We learned how engineers brilliantly use Michael Faraday's laws to run a generator backward as a massive starter motor. And we saw how the perfectly round geometry of the Powerformer's cables is reshaping how we push voltage across entire continents.
It is a testament to human ingenuity. I mean, the sheer density of problem solving happening inside these walls is breathtaking.
I want you, listening right now, to think about the device you are using to hear our voices. Maybe it's your phone, maybe it's your computer.
Whatever it is, it needs power.
Exactly. It has power because somewhere out there, right now, this incredibly complex, delicate ballet of explosive gases, heavy rotating steel, and synchronized electrical waves is executing perfectly every single second of every day.
It forces you to appreciate the invisible tethers of our modern world. And watching the trajectory of this engineering leaves us with a fascinating final thought.
What's that?
Well, we see Powerformers eliminating the need for massive oil-filled transformers. We see silent battery arrays replacing roaring diesel engines.
Right.
As we push technology forward, constantly hunting for more efficiency and fewer moving parts, we have to ask, are we heading toward a future where a power generation station doesn't look like a roaring mechanical beast at all?
Wow.
Will the power plant of tomorrow simply resemble a giant, silent, solid-state circuit board humming in the dark?
Silence and geometry replacing friction and fire. I love that. So the next time you walk into a dark room and flip that little piece of plastic on the wall, pause for just a second.
Yeah, take a moment.
It's not just on and off. You are commanding a mechanical titan miles away. Thank you for joining us on this deep dive. Keep questioning the everyday and keep learning.